Just a quick reminder, if you've parked a car here and you haven't given your license plate, you need to, because I think there are a lot of people who paid for parking permits and not very many that have actually given their license plates, and that's how they decide whether to give people tickets. So in the back, give the assistants here the license plate. You want to raise your hand? Yeah, so either of them, give your license plate to them and they can call it in for you. Okay, having said that.
Okay, my name is Wilbur Morning Gaskell. I'm chair this afternoon. And our first speaker is Casey here, and he's going to talk about galaxies in the Epoch of Reionization are all bark and no bite. That sounds pretty good. Plenty of ionizing photons, low escape fractions. Okay.
Okay. Thanks, Martin. I have my own. Can you guys hear me with this mic? Is that okay? Looking at people in the back. Yeah. Okay. Great. Okay. So it's great to be here today. I want to start off by thanking Rachel and the other organizers and hearing the history this morning about how we got here. I thought it was a great summary, just understanding how galaxies form at all, and the fact that even in 1984 they were already talking about galaxies at the epoch of combination, and then now we're going to start talking about galaxies that we've observed at the epoch of reionization with a telescope called James Webb that's already had its name mentioned a few times. And I'm going to use those data that we're getting to make some statements about the physical properties of these galaxies that are now being observed in and during and right after the epoch of reionization. So I'll start by thanking some of the people I'm involved with. This is work that's come out of a group of people working with the Sears team, which I will talk about briefly later on. I just want to highlight the contributions from Wada Hu, Justin Cole, and Lou Shen, all of them working with me at Texas A&M. Wada and Lou are both here, and they're giving talks later this week, so please feel free to talk to them about any of this stuff or you can talk to me about it. Okay, so I know it's often good to give a summary, just so you can go back to checking your email or whatever else you're doing on your computers. I'm sure you're taking notes diligently like they do in class when I teach. But here's the summary that I want you to walk away with. There are two key points. One, we're observing galaxies now at these highest redshifts, ones that we're actually trying to interpret their physical properties. We're doing it with imaging and also spectroscopy, and then we're modeling them in every which way we can using stellar population models. When we do that, the main things I want you to take away are, one, they have something called psi-ion, which is really a measurement of how many ionizing photons they are producing. That appears to be increasing both with redshift and also decreasing UV luminosity. As we go out to higher redshift, I'll show you some illustrations of that. We're seeing an increase in the amount of ionizing emergent radiation these galaxies are giving off. The second point I want to point out, though, is that one of the things that's kind of baffling at the moment, at least from the modeling, is that when you ask how much of that radiation is actually escaping into the intergalactic medium that would be sufficient to cause reionization, that seems to come out to be very low, and I'll discuss how we infer that. This is a model-inferred measurement. We're not measuring this directly, but we're trying to guess how much radiation is leaking into the IGM. It comes out to be a volume-averaged galaxy population average of about 3%. That's it. You can go back to whatever you're doing. This is, we submitted this into a paper that's currently under review, and it's on the archive. Please check that out. Okay, so let's give some of these details. All right, so what have we seen with James Webb? Well, prior to launch, people like Brant Robertson and many others were arguing that this quantity, psi-ion, which is a measurement and comes from stellar population models, it's the ratio of the rate of ionizing photons, so photons more energetic than 13.6 electron volts, to the UV luminosity. We're guessing from a stellar population model how many ionizing photons stellar populations would be giving off. The upper limit or upper expectation of what people expected is that this ratio in the log would be about 25.2. Brent has a great review article and some other previous articles about this. And that seems to agree, at least on average, with some measurements that were taken prior to James Webb out to redshifts of 3 or so. In the first couple of years of James Webb, what we begin to notice is that the galaxies we're measuring appear to have this ratio, psi-ion, as much higher than that canonical. Is anything going on? Okay. Technical difficulties. You don't like the button that says OK? Okay, we'll continue on. I'm not sure what that's about. There's a little button up here that no one can figure out what that's for, so don't touch it. Okay. Anyway, so the ratio, the James Webb observations are showing that the galaxies are giving off more ionizing photons than we may have expected prior to launch. Now, and this is a plot taken from Anthony Paul's work, but many other authors have seen something similar. This poses a problem in a very nice paper pointed out by Julian Munoz, and other people have seen this as well, that if they're putting out all of this ionizing radiation, much more than we expected, by a factor of 3 to 10, that if you start to ask the question, well, if we consider how much of that is leaking into the IgM, it would be too much, and reionization would occur too early. So this is an illustration of this fact. This is the hydrogen neutral fraction as a function of redshift, where the plot would show that the universe is very neutral out of these high redshifts. These are all these data points, and pre-James Webb models kind of fit this nicely when you combine the amount of ionizing radiation with the amount that's escaping into the IgM. Then when you start to consider the fact that, well, if James Webb is finding that galaxies out here have much higher psi-ion values, then suddenly you start to push reionization earlier, and depending on how much of that radiation leaks into the IgM, it can be pushed even earlier still. And so we thought, well, let's address this question directly. We can measure the amount of ionizing radiation. What do the galaxies tell us about their escape fraction? So we're going to look at both. And so we started doing this using imaging data and near-spec data from Sears and this other program, JADE, Brant talked about before. Here's an image that looks awful on the screen, but if you Google it, you'll find a better version of it. Here are the JADE's footprints. I won't talk too much about this, except that we have around 500 galaxies with sufficient spectroscopic data and imaging data that we could analyze them and make constraints on some of these features. Okay, so for people who are not initiated in this field, the way this works is you take a whole bunch of stellar population models, you combine that with various aspects of what you expect for that radiation propagating through the H2 regions that surround them. Here we're using this code called bagpipes, which is very flexible. You can program it and modify it in any which way you want. We're using the BPAS stellar population models. They include the effects of stellar binaries. They have their, stellar binaries that produce more massive stars that are doing all this mass exchange and allows for more ionizing photons to be produced. We have dust attenuation models. We vary metallicity, nebular emission. We've also included some other factors. And ones I'm going to really highlight are, we're using a flexible star formation history. This is from Kartik-Iyer's model, which gives a lot of flexibility in terms of how bursty or constant the star formation history has been over the past. We also introduced this function here, which allows for the fact that some of the radiation that leaks out from the stars may not be absorbed by the H2 region around them. So it's an additional factor here that basically says when you compute the radiative transfer, that the radiation is propagating through the H2 region, some fraction of that can escape. And so we end up lowering the nebular emission and the nebular continuum and the emission line spectra by this factor 1 minus F escape. Alexis Morales has a nice paper that describes this as well. The other aspect that we're doing for people who are familiar with observations is we're including both imaging, here's an image of one of our RGB image, and the prism spectroscopy, and we're doing it in a way that allows us to correct for any flux calibration problems. And a lot of this has to do with the fact that the galaxy, when you observe it with a spectrum, that's what these little shutters are here, you may not know exactly where it is within those shutters. And there are wavelength-dependent effects that deal with how much of that light makes it down to the detector. This is called a path loss correction. They are modeled by people at Space Telescope Science Institute, but we allow for the fact that we may have uncertainties in that, and as a result, the spectroscopy may not match the photometry. And so we've introduced this calibration factor. It's a second-order polynomial that allows you to correct the spectra to match the photometry, which we've measured in some matched apertures. People are worried about those things, in a way that allows us to model both the spectra and the photometry simultaneously, and in a way that is consistent. So as an example, here's that same galaxy again. Now I'm showing the photometry we have. We have this multi-band excellent photometry from James Webb and also from Hubble from previous observations, and also the spectra down here. And in both of these, the black points up here are the photometry, and the spectrum is shown down here as the gray. The green model here is the total SED fit after modeling over and marginalizing over all those different parameters. And so you'll see things like the emission lines. Here's H beta O3. Here's some other, I think that's H gamma. And oxygen 2 and neon 3 are down here. You'll also see very good fit to the UV continuum, and then we have a sharp break right around Lyman alpha, just as a result of the IgM capacity. And we can, these are both, it's the same model that's shown in both of these, just to illustrate that we are able to reproduce these. Okay. And from things like this, we can then begin to measure, for example, the UV luminosity. That's typically measured around 1,500 angstroms in the rest frame. That's just an illustration of that fact. And And then the other way you measure the ionizing production rate is that you simply take the flux in these measured Balmer lines. Most of the time we're using H beta. We can also use H alpha. They're very consistent, and I'm going to ask you about that later on. And you take the ratio of those two to calculate the psi ion parameter. The psi ion is literally this ratio. Basically interpret this as the strength of the Balmer emission line, converted into proper units, divided by the UV luminosity. And when we do that, here's our plot. So here's a plot of this quantity, log psi ion, as a function of the UV magnitudes. So bright galaxies are here, fainter objects are there. This canonical value of 25.2 is shown by that dot-dashed line or so. And then as we go out in redshift, or redshift 5, 6, 7, depending on the color coding. And the things to take away from this are the simple fact that as you go out in redshift, they appear to be moving up in this plot. And then as you go from left to right, they are also moving up. So fainter galaxies appear to have higher values of this psi ion, and that also seems to increase with redshift. Nevertheless, there is significant scatter. That's something else we can talk about, something I'll use later on when I try to consider the effects on ionization. Okay, that's psi ion. The escape parameter is more interesting. You have that little value. That's the OK button. It's blocking my thing. Okay, so this is one of our actual galaxies, but we're modeling this to see if we can recover and infer this escape fraction. And so the way it works is simply the following. This is real data that we're then simulating and perturbing to see the following effects. So here's one of our galaxies. And the way the escape parameter works is you're basically saying that if 100% of the emission is being absorbed by the H2 regions and then re-emitted in the emission line spectrum, you get the strongest possible emission. If you start to increase F escape, you're allowing more of those ionizing photons to escape. And as a result, you don't change the far UV continuum of the stellar population, or not much. There's a little bit of the nebular continuum in here. It's a small fraction compared to stars in this case. But you do begin to change the strength of the emission lines. And if you kind of squint, let your eyes go numb, you'll see we go from 0 escape to 10% escape to 30% escape. And the strength of the emission lines is declining as you do that. That's what's expected. And the question is, can you actually go and recover that? And we've demonstrated we can do that. These are actually some simulations that we show in this paper, I think in the appendix, that demonstrate we are able to recover these higher escape fractions. And this is just an illustration. So we can show actual data for this particular galaxy. That's shown here in gray. And then the best fit model in this case is in blue, and it favors a very low escape fraction of around 0%. That's this blue line. And then for funsies, we said, okay, if you force the escape fraction to be higher, in this case for illustration purposes, you make it 30%. That's this red line. And what you'll begin to notice, and especially if I kind of block it out, is that the biggest effect happens right in the region of the nebular emission lines. This is H beta 03. If you're somebody who worked with tech most of your lives, you probably are disgusted by how poor the resolution is here. For us, this is actually pretty good. You're seeing the 203 lines blended with H beta. And this is H alpha blended with nitrogen 2. But here, we're modeling all of those in a way that allows us to see that if the escape fraction was 30%, this model would very much under-predict the strength of the emission lines compared to the continuum. And so when we model something like this, we actually don't just get a best fit, we get a full probability distribution function from a posterior, and it would look something like this. This is the log of the F escape of this particular galaxy, and it really favors a low F escape. I mean, once you're below about 1%, convince yourself it's right, but it's something very close to 0 where higher escape fractions in this particular case are very much disfavored for this galaxy. When you look at the distribution, what you find is the following. So here, again, this is the log of the escape fraction here. So if you were at 100% escape, you'd be up here. If you're at 0, you're way down here at the bottom of the board. But this is 10% escape, 1%, 1,000%. 0.1%, excuse me. This is UV luminosity. So we have bright galaxies. We have faint galaxies sitting here. Again, color-coded by the same way. And this is all of our data. So there's about 500 galaxies. Most of the galaxies sit below this -2 line. So they favor very low escape fraction. That's what this modeling is telling us. Now, the data points are all the medians of those posteriors, and those posteriors are broad. And so that's what the error bars on here are showing you. They're showing you the 16th percentile up to the 84th percentile for objects. And so we do have objects. 3 minutes? Yeah, that sounds about right. Okay. So 3 minutes. Thank you. That's great. So here you have some objects that sit up here. They do favor higher F escape. And many of them have distribution functions that allow for some likelihood they have a higher F escape. And you can use all of that. But the medians all sit down here. We've got some fits through here, but they're all essentially saying that it's just flat, and we see no evolution either with UV luminosity or with redshift through here. One of the takeaways, though, is that if you were to use predicted relationships, so there's been a lot of work done at redshift 0.3, where you can measure this nearby, looking at properties of galaxies like the UV spectral slope, the UV luminosity, even the strength of emission lines, and correlating that with the amount of the Lyman continuum that is actually escaping, they would have predicted a relationship that looks like this at redshift 5, and it would actually be higher if you go to redshift 6 and 7. And we're very much inconsistent with something like that. And we're saying based on the SED modeling, there's no evidence that these galaxies have high F-escape values that would have been inferred using these low redshift relations. All right, so what does it say about ionization? I can do this in 2 minutes. Okay, so now we've done this. We've measured things like the distribution of psi ion. We've measured the distribution of F-escape. You can combine this with the UV luminosity function that people have measured to make inferences about the ionizing rate, the global cosmic ionization rate on average. This is just we've gone through this exercise. So we simulate the UV luminosity function using what we can get. We can make as many of these iterations as we want. We measure the distribution of psi ion as a function of UV luminosity. We measure the distribution of F-escape as a function of UV luminosity. We can begin to fold that through and say things like, what is the volume average escape fraction of galaxies out at these redshifts? That's what these points are. To do this, you have to integrate the UV luminosity function down to a certain value. And then when we do that down to what we can see, we get values that look like this. That's 3 plus or minus 1% with very little indication of evolution. It's consistent more or less with what various simulations show us all here, and it's inconsistent with what we would see from using these low redshift relationships. Give the punch line. So then we can go and say, okay, what does this do for the ionized fraction of the universe if you propagate this through the differential equation that shows how it evolved? You can take those same results and do this. This is what we would get if we only integrate down to minus 16, which is where we can observe the galaxies. And here we would find that you reach a 50 percentile point somewhere between redshift 5.5 and 7.1. But that's only for these bright objects. And compare that to what Planck and Peterson-Soph would say, and it's more or less consistent with the tail of it. If you try to extrapolate to lower redshift galaxies, well, then the sky's the limit because we don't really know what the properties of all of these fainter galaxies are. But we would say that it's certainly, you haven't broken the universe. And so I think that the astrophysics is more or less taken. There are some problems, but I will ask you about any of this stuff later on. These are things we're considering about how to improve upon this or questions that we think we need to ask. And then I'll summarize it here. So the things to really take away is that when we look at the galaxies in the reionization epoch, we're finding that the psi-ion value is high and looks like it's higher, at least for these galaxies, compared to what we would have predicted pre-James Webb. But the escape values are low, and so when you combine those two things, reionization seems to occur in the rate. Stop there.
Okay, well, thank you very much. We have time for a 30-second question that only needs a 30-second answer. Let's go to Joel down here.
So many simulations have shown that the galaxies that are most likely to have high escape fraction are very low mass galaxies, low luminosity galaxies, which you are probably not observing.
Not at all.
So
Right.
how can we take that into effect? Is that the part of the solution to understanding the connection between the observed reionization and this very small escape fraction that you're seeing from more luminous galaxies?
Yeah, no, that's a great question, Joel. I think the answer is yes. We're only seeing things down to minus 16. We don't know the properties of the lower mass galaxies. The ones that have been detected are probably very biased towards things with strong emission lines. They are seen there. I think that's where a lot of work needs to be done.
Okay, so let's thank Casey again.
Thanks, Martin.
And then we'll do the switch over the lapel microphones and the next computer in there. And are you sharing or not yet? You might have to share your screen.